we have considered ideal that is if we transmit ST then
Sir, are you sharing your screen?
yes,
Can you?
yeah, I'll unshare and reshare it. Visible now?
Yes, sir.
Right? This is what we have considered till now.
Yes, sir.
And talking about the complex baseband equivalents. Letting ST just we have defined the low pass equivalent with a slightly different symbol. Agreed?
Yes, sir.
Now channel. So basically now let us look at the right. So there are two types of communication channels. Can you name them?
Wireless wireline.
Yes. Wireline. Fine. So now if I talk about a wireline channel, say, have you heard of in your electromagnetics course, did you discuss wireline channels or wired signals, wired channels? No. Okay. So can you give me an example of a practical wireline channel that you have seen?
Sir, LAN.
Yep.
I mean the
LAN.
LAN wires.
Huh?
Optic fibers communication.
Optical fiber is a different ball game. We won't go there. Okay. I'll consider something that is much simpler than optical fibers because optical fibers use completely different ideas. So
So
let's not.
telephone line.
Yeah, telephone line. So the simplest one would be, so did any one of you have those Doordarshan antennas, Yagi Uda antennas at the top of your house? Okay, no one saw.
I-
Has anyone seen a Yagi Ude antenna on the top of their house?
Yes, sir.
Okay, you haven't. No problems. Has anyone heard the term Yagi Ude antenna?
No, sir.
Something that seen anything like this? No, no problems. So let's consider a telephone line. Simple, slightly old-fashioned. It is a twisted pair cable. So if you look at the LAN wire, it contains 4 such twisted pairs. Or Ethernet cable, LAN wire, Ethernet cable has 4 such twisted pairs. Now, what do twisted pairs mean? That 2 copper wires fine, something like this. Agreed? Has anyone opened the Ethernet cable?
Yes, sir.
So you might have seen twisted pairs inside, right?
Yes, sir.
So so this, so what, so 2 copper wires that are overlapped with each other. What does this mean? This twisted pair. So this means that long, thin copper wires. Fine. What does a long and thin wire imply? Anyone?
More resistance.
Yes. We did this in class 12, right? Two
Yes, sir.
twisted wires. What does this mean? They're twisted just to hold them together. But uh, what, so what would twisting a wire do to it?
No magnetic field.
What?
No magnetic field.
Anything else that it would cause? What is this? This is a
So,
twisted wire.
yes, sir.
And what else is this?
Inductance.
Magnetic.
Yes, inductance. And 3 pair of wires separated by rubber, right? That is rubber. That's a pair of wires separated by rubber. You agree? Guys?
Sir, it's still loading in my.
Okay.
Oh.
No, I haven't written anything. So it is a pair of wires separated by rubber. You agree on that?
Yes, sir. What?
So what is rubber?
No, sir. What is the? I mean, what are you describing? A twisted pair.
Yes, a twisted pair inside a
Yes.
Ethernet cable.
Okay.
Right. So that is a pair of wires separated by rubber. And what is rubber? It is a
Insulator. Insulator.
dielectric. Dielectric. Let's be slightly more technical. So, and what happens when you place a pair of conductors and separate it with a dielectric?
Capacitance.
Yes, capacitor. So a twisted pair or a twisted pair of cables has the characteristics of all three basic passive circuit elements, R, L, and C. In general, a twisted pair have all these effects and two-port. We can see it as a two-port network.
Yes, sir.
Yes.
We can see the input. We can therefore see this wired communication channel as a two-port network.
Yes,
And
sir.
let the channel will have some frequency response, say, and therefore some time domain response. Agreed?
Yes, sir.
Similarly, case of wireless so when we talk of wireless communication, actually this is a good point to introduce this. So when we talk of wireless communication, there are two types of wireless communication or two types of wireless links, LOS channels and non-line of sight channels. So when I say LOS, line of sight, transmitter, receiver, transmit from here, and the receiver can see the transmitter, and because of that it is able to directly pick up the wavefronts generated by the transmitter. This is called line of sight link. We have discussed this. Fine.
Yes, sir.
Nothing fancy about it. But at the same time, can you always see the mobile phone tower when you are talking to anyone or when you're using the data?
No, sir.
Can you always see the Wi-Fi router when you are accessing your home's Wi-Fi? Obviously, you notice that the quality of Wi-Fi improves significantly if you, or the quality of a Wi-Fi link improves significantly if you are in direct line of sight with the Wi-Fi router, but Wi-Fi still works without the router, right? Or without you being in the same room as the router.
Yes, sir.
Yes. So apart from line of sight links, there are something called non-line of sight links that dominate our wireless communication uh, or wireless communications. And these are via three medium or three media. Reflection. So example, since we are talking of about electromagnetic waves, uh, do you always need to see the sun to get sunlight?
No. No.
Reflected light can be, so the moon actually is a good example of reflected light or
Yes,
reflected
sir.
source of light. Two, scattering. Before we see sunlight, the scattering of light due to atmosphere lights up the entire sky as blue, or lights up our entire atmosphere as blue, right?
Yes, sir.
Plus, right now, even if I switch off the lights in my office, I will still get scattered and reflected light from the trees and the roads outside. And this should be B. Agreed?
Yes.
C. So guesses about C? C is slightly
Bending.
non.
Diffraction.
Hey, you have done the wireless course. Don't spoil it for others. Yeah, diffraction. But what you would say is that we generally don't see diffraction in visible light because so scattering and reflection are easy to explain via the analogy of visible light, but diffraction. So the thing is that bending or diffraction, if you remember from your class 12 physics course, that this is the bending of light, red electromagnetic waves. When it encounters obstacles that are comparable, it's this is if we remember correctly, this is what we define diffraction as, right? So now let us look at wireless comms. So we operate at frequencies close to, actually we work around 300 megahertz to 3 gigahertz. We work in this range. So 3 into 10 to power 8 to means the wavelengths of the light of light that we are working with are in the range. What will be this range? Right? 10
Yes,
centimeters
sir.
to 1 meter. So, and there are a lot of objects which are of the order of 10 centimeter to 1 meter outside your window.
Yes, sir.
So when light hits these objects, it will bend as well, or when electromagnetic waves within this wavelength hit these objects, they will bend. Makes sense?
Yes, sir.
So there are three non-line of sight propagation media: reflection, reflection, bending, and or reflection, scattering, and diffraction. Now,
Sir, what is the difference between scattering and diffraction?
scattering and reflection. So
Sir,
reflection follows Snell's law. No, Snell's law is for, so reflection follows that angle of incidence equals angle of reflection. Those kind of laws. Scattering is in any general direction. Spreading of light in any general direction.
okay, sir.
Okay. Or reflection, generally we consider it from smooth surfaces, and scattering is simply light impinges on something and it spreads out in all directions. That's why we say, that's why I gave the example of the moon. So the moon is a reflecting surface, or the moon acts as a reflecting surface, whereas the atmosphere acts as a scatterer. Right?
Okay, sir.
So now, say this is the transmitter, and this is the receiver. And this is obstacle 1, this is obstacle 2, this is obstacle 3. Of course, this is a simplistic depiction. It will be, everything will face multiple reflections and scattering, but there are multiple indirect paths to the destination, right? Makes sense?
Yes, sir.
So now, basically, if I transmit pulse, say I transmit delta t here, then this path will have some delay. It will give me, I'll receive delta t minus tau 1 from this path, or say alpha 1 delta t minus tau 1 from this path, alpha 2 delta t minus tau 2 from this path, alpha 3 delta t minus tau 3 and alpha L delta t minus tau L, right? So the impulse response fine.
Yes, sir.
Good. So, but we won't talk about detailing this impulse response now. Maybe we'll talk about it once we reach the point where we discuss impulse responses. So anyway, the point is that both wired and wireless channels will have an impulse response, right? And RT or RLT equals CT convolved with VT plus, right? This is what we will practically receive. You guys agree with this?
Yes.
Yeah, great. So others, this makes some sense. Others, guys,
Yes, yes, sir.
have I
This
lost
is what.
everyone else? Yeah,
Yes, sir. This is what we will receive.
yes. So, and I can,
Sir,
yeah,
sir, we will be sending modulated signals now.
yes.
Then why are you convolving baseband signal with channel?
So if you go back when we talked about baseband passband systems, we talked that we can represent passband systems with in terms of their baseband equivalents as well.
Yes, sir.
Fine. So this is the baseband equivalent of the channel. We developed baseband equivalents because it's easier for us to look at everything in terms of baseband equivalents.
Okay.
Fine. So I can define fine. and the delay for channel is said to be non-distorting if CF is constant and theta f is so you have talked about linear impulse response in DSP or linear phase in DSP, right?
Yes, sir.
Yes. So did anyone question the need for a linear phase? That this was people shouted again and or people said again and again, see, FIR filters are better because they have a linear phase response or linear phase response, but IR filters are not good because they can have a non-linear phase response. So can anyone tell me why this is important or why linear phase response is important? Yes, Adit?
So now I was trying to think.
Yeah,
Sir,
think.
sir,
Yeah, Panindra.
sir, if we have a linear phase after filtering, the waveform would be having just will be having a delay. The waveform would not be changing, but if we have a non-linear phase, then after filtering, there would
How
be
will the waveform
changes.
change? How will the
So
waveform
change
change?
means that like sir showed some diagrams at that time.
Okay,
There was
I'll
just
instead of diagrams, let me give you some common
Yeah.
logic.
So for example, if we are sending sinusoids, then at different time intervals, the amplitude of the sinusoid may be affected due to the different phase. So that may transform the sinusoid to something else. So
No, no, no.
that's
Okay,
why
so sinusoid is a pure frequency.
yeah, I mean it's
Sinusoid is a pure
not
frequency. So let me
any square.
put it like this. You have a song, pick any song of your choice. So a song has so music, for example, makes sense when so you have three kinds of instruments, suppose, or there are so there are drums around 100 hertz, vocals around 1 kilohertz. There is the what do you say organs or air instruments, wind instruments, say flutes around 10 kilohertz and or say 5 kilohertz and string instruments around 10 kilohertz. Music people, are these approximate ranges correct? Music club? Anyone? Oh, no one from music club. Sad. So let's say these are the approximate ranges. I tried to get them correct, but I do not remember. So this. So now, what happens if the sound of the drums reaches you early, the vocals reach slightly later, the flutes reach even later, and the string instruments reach you the latest? Different frequencies or different frequency ranges, and the delay for these frequency ranges will be different if the phase response is nonlinear. Agreed? You agree on that? Guys?
So could you repeat?
So yeah, so there is some unwanted noise today outside my office. I don't know why. So what I was saying is that if you are playing some music, and what happens is that due to the nonlinear phase response, the drums reach you early, the vocals reach slightly later, the flute reaches even more later, and the string instruments land somewhere in between vocals and drums. Would you still call that music, or will that be noise?
Sir, it would definitely be noise.
Yes, it would be noise. So, and this happens when the delay for different frequencies is different.
Yes.
This happens. So, which means that this happens when the phase is nonlinear. So you have an idea of the kind of trouble a nonlinear phase response is capable of causing. So this is why we
So, but,
emphasize so much
so,
on a linear phase response. Fine.
sir, but
So
I mean, this is a characteristic of the channel, right? We can't decide or we can't tune it.
so yeah, so
I
that's
mean,
what a channel is said to be non-distorting.
oh, okay, okay.
I just sidetracked the discussion with that importance of linear phase in DSP, because that's the whole reason we go for FIR kind of filters. Fine.
Okay, sir.
So now what we have is RT equals T plus, but considering PAM like, or even QAM VT equals summation we use the symbol IN G T minus NT N equals minus infinity to infinity. Fine. This is what we have talked about till now. IN can be complex valued. Fine. So now RT equals summation n equals minus infinity to infinity in CT plus fine. This is okay. Guys,
Yes, sir.
let RT be processed using a post-processing filter PT equals n equals minus infinity to infinity in convolved with CT convolved with plus eta t convolved with PT minus to infinity in x t minus nt plus, say, let's call this beast fine. This is fine, guys.
Yes, sir.
Now post-processing with PT, we sample the signal at MT to get x MT minus NT plus W MT, or Ym equals summation to infinity x x m minus n plus equals in x im x n m minus n, or im x0 plus summation n goes from minus infinity to infinity and not equal to m. Right? Is this okay?
Yes, sir.
Yes. So yeah, I'm sorry about that noise, but what can we do? Yeah. So now, in an ideal world, want ym equals im plus, right? This is what we want, or this is what the ideal channel looks like that we discussed earlier. Or the channel that we have used till now looks like this. So whatever we have actually considered till now, whatever considered till now corresponds to the case where x0 equals 1 and xk equal to 0 for. You agree on this?
Yes, sir.
I can say that the value of x0 is the gain for the gains or attenuation desired component and xk for k not equal to 0 lets in interference from other symbols sent over the, right?
Yes, sir.
So therefore ym equals x0 im plus summation n goes from minus infinity to infinity and not equal to m im in x m minus n plus This has three parts, or I can write this as desired signal, additive noise, this is what is known as intersymbol interference, or shorten it to ISI. Fine. So this is what is known as ISI, or intersymbol interference, and what we want is zero ISI. Right? That is,
Yes, sir.
we want XM, or Xn equals delta n. You want the sequence Xn equals this, but Xn equals Pt convolved with Ct convolved with Gt, right? Makes sense? Or this is Xn, and out of these, Pt is the receiver processing, Gt is the transmitted pulse shape, Ct the channel pulse response. Fine. So let's look at these one by one. Can we control receiver processing waveform? Can we control the receiver processing waveform? Anyone?
Yes, sir.
Yeah. So we can control the receiver processing waveform. We can control the transmitted pulse shape. Can we control the channel impulse response?
No, sir.
We cannot. So the purpose of our discussion in the coming lectures, because it's almost time, I won't proceed from this point. The purpose of our discussion in the coming lectures is to design PT and GT so that for a given channel impulse response, we are able to extract the signal with minimum amount of ISI, or with the minimum amount of intersymbol interference. Fine.
Yes,
So
sir.
we would stop here and continue the discussion on ISI and band limited channels on Tuesday. Bye then. Have a nice
Okay,
weekend.
sir. Thank you, sir.